like this. Magnetic field of rotating charged disk. Kind of, it's the same process that we do for electric fields. If you notice it, oh, here's me. Okay, it's the same process that we do with electric field. Is we do the electric field of a ring, then we do electric field of a plate, right? It's the same idea. So then this plate is rotating. And oh, donut, that would be nice. If you think about it, this is the mechanism of how we get magnetic field here on Earth. If you look at the interior of the Earth, essentially it's a convection plate that's rotating, right? Magnetic field of Earth due to Earth's interior, due to Earth's interior dynamo effect. You see? The dynamo mechanism is showing how planets and stars create strong magnetic fields. You see? So this is our computer animated models of how magnetism is created inside the core of planets. You see here? You got it's almost like a solenoid like, you see that? The vortex. See how it goes, creates it like this, like that, and it creates a magnetic field like that, going out and coming back in. So it's almost like you have a bunch of solenoids. You see that, according to that model. Wow, I like that picture. Like almost like 3 huge solenoids. And then these are rotating. That's how they're creating the magnetism, you see? I like that picture. No, the other one was better. Let's see this one. Oh, okay. Let's see. So I always like to tie it to other things that, so we can see, you can kind of see here. Oh yeah, you see this loops? A bunch of solenoids. You see the current, that's why we have a liquid outer core. It makes the magnetic field even stronger because the outer core of the Earth's interior is liquid. So it can flow faster. So you got a large, strong currents like that. That's where the magnetic field is created from the liquid core. Sun's dynamo effect is much stronger. Magnetic field due to sun's interior. Sun's. On the sun, you have even more of an effect because since the sun is a gas, look at all the loops that are made. Really active, you see here? And the sun doesn't rotate in the same pace everywhere. So it's like all these strong magnetic fields, all these currents are created inside the sun. Yeah, cool. So that's why it's kind of when we're learning the plate, we're learning how to analyze. See, when we're doing the solenoid and the plate, we're learning how to analyze all kinds of weird scenarios. So you can have a charged plate like this, and then it's spinning and it's made up of a bunch of rings, you see. So what was the equation that we derived for the magnetic field of, let's see, what was that? So this was the general equation that we derived for the magnetic field of a coil, a certain distance away. We use that to derive the magnetic field of a solenoid. So that's going to be our equation to also do the plate. So let's write that equation. dB is mu 0 di r squared over 2x squared plus r squared to the 3/2. Right? So we're going to use the same techniques that we did when we did electric field of a plate, right? So we're going to say, let the surface charge density be, so let's say this has a certain charge, the plate, and let's say it's spinning with a certain frequency f, right? And then we're going to say, the current charge divided by the period is going to be equal to the current, right? So then di is going to be sigma dA and then you have a certain point here, and dA is going to be 2 pi r dr. So dB is equal to mu 0 sigma over 2, and then dA is going to be 2 pi r dr r squared over x squared plus r squared to the 3/2, 0 to the big radius. So I'm doing a constant uniform charge plate. So di is sigma dA, sigma, then you're going to have sigma is going to be the total current of the plate divided by the area of the plate. And you're going to have here 2 pi 0 to r cubed dr over x squared plus r squared to the 3/2. Let's see if we can get a general equation of that. So this will be the general equation of charged plate any distance away. So you're going to have 2 pi r dr. So we have r cubed. Okay, back to the integral. Today we use the integral a lot. R to the power 3. Well, I'm going to make my variable r. R to the power 3. And then here you're going to make it x squared plus r squared. This is little r squared. Okay, so let's look here. Did I put it in right? R cubed over x squared plus r squared to the 1/2, right? And then 0 to big R. No? Oh, it doesn't recognize the capital R. That's fine. Okay, that should work. Oh, it's weird. . that the final answer? The, I guess so. Okay, so then you're going to have B mu 0 I over 2a 2 pi. So we have r squared plus 2x squared over square root of r squared minus plus x squared minus 2x. So I changed the little r to big R because it was the radius of the thing. So that's the final answer came out to be that. So then 2 cancels the 2. And then here you have area is pi r squared. Pi r squared. So pi cancels the pi. And then you just have mu 0 I over r squared plus 2x squared over square root of r squared plus x squared minus 2x. Okay, it'd be nice to see if we, let's see here, if this current had, see, remember earlier we had that wire and the current was 1 amp, the radius was 1 meter, and the number of turns was 1, right? And we saw that the magnetic field in the center was what? 6.28 times 10 to the minus 7 Teslas. So now if you have the whole plate current of 1 amp, right, flowing like that, then what would be the field right at the center? We could kind of compare the two and see if it makes sense. So this is valid for any x distance away from the center. So if I put x is 0, right? If I put x is 0, what do I get? This disappears, this disappears, this disappears. Oh, then you get the magnetic field at the center is what? This is gone, this is gone, this is gone. So mu 0 I over r squared. And then this is gone, this is gone. And then you get r over, no, r squared over, and then this is square root of r squared, so that's just r, right? And then this is gone, right? Yeah, and then this is gone. Okay, so then it's just, this is 1 meter, so it's 4 pi times 10 to the, and this is 1 amp too, 4 pi times 10 to the minus 7. Oh, and then this one was what? 2 pi times 10 to the minus 7. Oh, okay. So this is twice as strong. So if it's a complete plate, the field there is twice as strong as if all the current is at the edge. You see that? So it would be twice as strong as that. 12.56 times 10 to the minus 7. Okay, that makes sense. So you see, always that's the other thing that I like doing. Driving an equation, seeing if the equation makes sense, then seeing if the answer makes sense. Yeah, so if the whole thing has a current, and the field there should be stronger because it's closer to where the current is, versus if all the current is only at the edge, you see. So yeah, it's twice as strong as if the current is only at the edge. The other way that this kind of a problem can be given is you could say you have a charge plate of 1 coulomb and it's rotating with a frequency of 60 cycles per second, let's say. Then how do we interpret that in terms of this equation? You can still use this equation for that too. So what you do is you say B is mu 0 and I is just the Q over the period. That's kind of what I was showing here earlier. The current is the charge divided by how long it takes the charge to make 1 revolution. Then you say 1 over the period is its frequency. You see? So if the charge is given to you, the charge of the plate, and the frequency is given, then you can just call the current QF. So then it just becomes mu 0, and then the current becomes QF over R squared. So now if I want to find the B field at the center, and of course it's going to be the same equation, so then it's just going to be mu 0 QF, and then here's just going to give you R over R squared, and then the R is going to cancel. And if the charge is 1 coulomb, the radius is 1 meter, but it's 60 hertz. Oh, that's going to cause a much stronger field times mu 0. Right? So the idea of that is that if you spin it faster, if you get a charged plate, the faster you spin it, you can have it create very strong fields for you. If you spins at 100 hertz, 200 hertz, imagine 1,000 hertz, you can have it create very, very strong fields that are very noticeable, you see? You could even do this at home, maybe. Just charge a plate, you know, charge it with some static charge, and then have it spin, you know, on some mechanism. Have it spin, and then put a compass near it and see if the compass reacts to it. It should. The faster you got it spinning, like on some kind of rotating thing, you know, as long as you got some static charge on it, have it spin very fast, and then the compass needle should point this way. You see, in the direction of the field, like that. So you should see it react to the field of the plate.